Good. So, okay. So today we have the pleasure to listen to Cristina Urbani from Roma Tor Vergata in Italy, and she will speak about a constructive algorithm for building mixing copying potentials. Thank you.
Okay, thank you for the presentation, and thank you to the whole organizer for the kind invitation. It's a pleasure to be here to give a talk. So the topic of my talk will be a result obtained in collaboration with Professor Alabau, and is about the analysis of an hypothesis that arises when dealing with bilinear control systems, and in particular when the strategy to prove controllability relies on a linearization argument. So let's see the outline of the talk. First, I will give an introduction to bilinear control, recalling all the main features. Then I will go to the motivation of our study. Then I will present our algorithm. Then I will show you some application and examples of potential that come from our algorithm. So let's go for the introduction. We have a control system that is a dynamical system in which the dynamics is described by a function of the state U and of the control P. And the control is the function on which we can act to steer the solution of our equation to our target state. So what does it mean that this control system is locally exactly controllable along a given trajectory? It means that given a positive time and given an initial state U0 and a reference control P bar, we compute the solution of our equation. And this will be the reference trajectory along which we want to control our problem. So if our problem is locally exactly controllable, this means that for any epsilon, there exists a delta such that for every initial and final state chosen in a neighborhood of the initial condition U bar and the target state ut of U bar t, there exists a control that is close to our reference control P bar such that the solution of our equation in U0 at time capital T reaches UF. Depending on the position of the control in the system, we have different kinds of control system. Here we have additive control that can be boundary control problems if the control is at the boundary, or locally distributed control system if the control is an additive term. Then we can have another kind of control system that is called the multiplicative control system, where the control enters the equation as a coefficient of the equation. And the main difference between this kind of control system is that the map from the control to the solution of our equation is linear in the first two cases and non-linear in the third one. So we cannot use the well-known theory for linear controls, like the duality between observability and controllability, or the Hilbert uniqueness method. And the strategy that is usually used for this kind of system is to linearize along the trajectory, try to prove the controllability of the linearized system, and then somehow try to deduce the controllability of the nonlinear problem from the linearized one. But there is another obstruction in dealing with this kind of control system that is represented by the famous theorem of Ball-Marsden-Lemrod that says that under very general assumption the operator A and B, namely A is a generator of a strongly continuous semigroup and B is a linear bounded operator, then from any initial state in the space, the reachable set has a dense complement. This means that we cannot hope for this kind of controllability results. And there are two ways that has been found to prove some results of controllability for this kind of control system. One is due to Professor Bouchard, and she succeeded in proving controllability result by violating one of the hypotheses of this theorem, and indeed she proves the results of controllability in spaces where B results to be unbounded. The other way we have found to prove results of controllability, and in particular for parabolic system, parabolic equation, is to reduce the reachable set to a point. So we cannot, we do not violate the theorem of Boltzmann and Lemrod because our reachable state collapses to a point, and we control our equation exactly on the reference trajectory. Okay, so the hypotheses we use on the operator A and B are the following. For A, we choose a densely defined linear operator, self-adjoint, such that A plus sigma identity is a positive operator with compact resolvent. And we will call this hypothesis the Coffee condition. Then for B, we have taken a bounded linear operator, and the problem we deal with is the following one, is the bilinear control system in which the control is a scalar function of time. So it's a very weak control. And the trajectory, the reference trajectory we control to are the so-called eigensolution. That means that are solution of our problem when P, the control, is equal to 0. So we have just the free dynamics, and the initial condition is an eigenfunction of the operator. We introduce this definition. So if A satisfies the Coffee condition and the pair and B is a bounded linear operator, we say that the pair AB is j-null controllable if there exists a constant n that is called the control cost, such that for any initial condition on the space, we can find a control that is bounded by a constant time the initial condition, such that this this linear problem here, when using this control, is null controllable. It means that it has been driven to the zero state. So under this condition, we have proved that our bilinear system is super exponentially stabilizable to any eigensolution Pj. This means that the solution approaches the eigensolution Pj with a double exponential rate of convergence. So the convergence is very fast. Moreover, strengthening a bit the hypothesis on the operator A and B, we proved that if the control cost satisfies also this behavior here, so it is less than e to the power a constant over t, then we reach exactly the eigensolution phi j after time capital T. Then we gave sufficient condition for the property of j-null controllability to hold. Indeed, if A satisfies the Coffee condition and also the eigenvalues satisfy this gap condition, and B is a bounded linear operator such that the Fourier coefficient of B phi j are all different from 0, and this series converges for some tau positive, then the pair AB is j-null controllable. And moreover, to have the exact controllability result, so to have the control cost satisfy this further assumption, we need that A satisfies always the Coffee condition and the gap condition on the eigenvalues, and B satisfies that the following assumption, that is, the Fourier coefficients of B phi j are all different from 0, and furthermore they are bounded from below by a constant time the eigenvalues lambda k to some power q. Now we move to the motivation of our work. The motivation is the following. We have seen that an hypothesis that is necessary for proving the j-null controllability and then the stabilization and controllability result is that the Fourier coefficient of the operator B applied to phi j must be different from 0 for any k in the natural number. But this hypothesis comes also in other work. For instance, here we have the work by Bouchard and Laurent for the controllability of the 1D Schrödinger equation with bilinear control. Their operator B is a multiplication operator by a function mu, a potential mu, and they control to the first eigensolution. And again, we see that the same condition of the eigenvalues must hold. So they must be different from 0. The condition on the Fourier coefficient of mu phi 1 must hold. And here we have another result by Bouchard for the controllability of the 1D wave equation. And again, she controls the solution again along the first eigensolution, that in this case is phi1 equal 1, and the Fourier coefficient of mu phi 1 must be equal 0 even in this case. So we have seen that a common hypothesis that arises for a bilinear control system is that the Fourier coefficient of mu phi 1, if the operator B is a multiplication operator by a potential, must be different from 0 for any k. And we will call this condition here NVFC, that stays for non-vanishing Fourier coefficient. And however, even if in some works it is proved that this condition holds generically, there are few examples of suitable mu that fulfill this condition here, and usually it is a polynomial of lower degree or low degree, for instance x or x squared, but no more examples are given in literature. And moreover, the examples that are given are based on the explicit knowledge of the eigenvalues and eigenfunctions of the operator. So our goal has been to define an algorithm that means to give sufficient condition for building this kind of potentials that satisfies the non-vanishing Fourier coefficient condition. And so we could provide more examples of potential that are suitable for these problems. And moreover, we could extend controllability results to other boundary conditions for which the eigenvalues and eigenfunction of the operator A are not explicit. So the first point was to prove this key formula for the Fourier coefficient of mu phi 1. So we consider the one-dimensional Laplacian with some boundary coefficient that for now we do not explicit. And we see that the Fourier coefficient of mu phi 1 are given in terms of an integral part that involves the fourth and the second derivative of mu, plus boundary terms of mu and its derivative evaluated in 1 and 0. Now we iterate this formula and we prove that for smoother mu and for any n in the natural number and any k greater or equal than 2, the Fourier coefficient of mu phi 1 are given in terms of an integral part that involves high order derivative of mu, the lowest one being mu to the power 2n to mu to the power 4n, plus a boundary term here. In order to better rewrite this last part, this boundary part, we introduce this function capital R. And we show that if you take mu to be a polynomial of degree q and you choose n to be such that 2n is greater than q, then the scalar product mu phi 1 phi k is given only in term of the boundary part when this function R appears. So why the integral part here, oops, disappear is because we have chosen n greater enough such that a polynomial of degree q have the derivative of order from 2n to 4n that vanish because 2n is greater than q. So we remain just with the boundary terms where this function capital R appears. And the nice thing that we have found is that actually we know the sign of capital R depending on the index small r. And indeed, we proved that for even indices, capital R is strictly positive, and for odd indices, capital R is strictly negative. For any alpha greater than 4, and we have proved that actually in our case, we have this condition satisfied. So our algorithm use deeply the knowledge of the sign of capital R. Now we choose some boundary condition. For instance, we choose Dirichlet condition on one side and Robin condition on the other side, so that the eigenvalues and eigenfunction are not explicit. Indeed, one can prove that eigenvalues are the square of these numbers Rk, that are the positive solution of this equation, and the eigenvalues are given by a normalization constant time the sinus of Rk. So as you may see, they are not explicit. We apply our formula to this particular kind of boundary condition. So we have the scalar product, the integral part, and the boundary terms that we will call dkn. Now we introduce this coefficient AR, BR, and CR that are a linear combination of the derivative of mu. And it is possible to prove that for any set of coefficient AR and BR, it is possible to determine a unique polynomial in the space of polynomials of degree q and 0 lower order term, and the derivative are given by linear combination of this coefficient. Vice versa, for any polynomial in this space of polynomial of degree q and 0 lower order term, the derivative in one completely uniquely determine the coefficient AR and BR. So our algorithm will produce coefficient AR and BR. From this coefficient, we can compute the derivative of mu in 1, and then finally, thanks to the finite Taylor expansion of our polynomial, we can define our polynomial. Actually, our algorithm will build just this part because the zero order term will be computed at the end of the algorithm by imposing that also the first Fourier coefficient mu phi 1 is different from 0, because the algorithm deals only with the Fourier coefficient mu phi 1 phi k with k greater or equal than 2. So if we take mu to be a polynomial of degree q, then the boundary term, if you recall, we called dkn, can be divided in its even term and odd term that can be written in this form here, where the function capital R appears. So the strategy is the following. If we want the Fourier coefficient of mu phi 1 to be different from 0 for any k greater or equal than 2, this is equivalent by choosing 2n greater or equal, strictly greater than q, to require the boundary term to be different from 0 for any k greater or equal than 2, and this is equivalent to require the even and the odd part of dkn to be different from 0 for any I. So how we did it? We used the R is positive for even indices. So for even indices, we produce the coefficient AR and BR, because this function G depends on the AR and BR. So we produce a coefficient AR and BR such that this part here would be strictly positive. And for even indices, odd indices, capital R is negative, strictly negative. So we produce AR and BR such that this part is strictly negative, so that the product will be always strictly positive and the sum remains strictly positive. So we have produced AIN strictly positive and in particular different from 0. So this is the algorithm. The input will be this constant here that depends only on the first 3 eigenvalues of the operator that can be computed numerically. Then the algorithm works a cascade, namely we first define the coefficient AL minus 1, BL minus 1, and then we go down to compute, to define the coefficient AR and BR for R that goes from L minus 1 to 0. So we first compute AL minus 1, BL minus 1, choosing them in these intervals here, where M1, M2 depends only on the inputs. Once we computed AL minus 1, BL minus 1, we enter in this loop here, where we compute AR and BR with R that goes from L minus 1 to 0. And at each step, we choose AR and BR in these intervals when this coefficient here depend on the input and also on the AR and BR previously computed. So at the end of the algorithm, the output will be the set of coefficient AR and BR, from which we can compute the derivative of mu in 1, and we can define this polynomial in the space of polynomials of degree q and 0 lower order term. Finally, we can compute the 0 order term of the polynomial by imposing that the first Fourier coefficient is different from 0, and it is done by choosing a constant that is different from the integral of this polynomial here times the first eigenfunction to the power 2. So our final polynomial that satisfies the non-vanishing Fourier coefficient property is this one, the sum of the the 0 order term plus the polynomial that comes from the algorithm. Now we'll show some application. Here we consider the 1D Schrödinger equation that models a quantum particle subject to an electric field, and the magnitude of the electric field will be represented by the control P. Mu is the dipolar moment of the particle. And we put this particle in a box where on one side we have Dirichlet boundary condition that represent a perfectly reflecting wall, and on the other side we have Robin condition. The Robin condition here represent a non perfectly reflecting wall. It means that the coefficient that appears in front of the first derivative is the time delay in scattering, that is the difference between the moment of incidence and reflection. And so it depends on the materials of the wall. So we could prove the controllability of the Schrödinger equation with mixed boundary condition, and it is very similar to the result of Bouchard-Laurent for the Schrödinger equation with the Dirichlet boundary condition. The only difference here is the power of lambda k. But the nice thing was that if you pick mu from our algorithm, then we could prove that this property here is automatically satisfied. So the theorem reads like this. If you take a polynomial of degree q that comes from our algorithm, then you have the controllability of the Schrödinger equation. Finally, I want to show you some polynomials that come from our algorithm and that satisfy the non-vanishing Fourier coefficient property. Here we have a polynomial of degree 5, 6, and 7. And as you may imagine, if you have to compute by hand the non-vanishing Fourier coefficient property, it would be a nightmare to integrate by parts, like an amount of time that is a nightmare. So through our algorithm, you are safe that this polynomials satisfies the non-vanishing Fourier coefficient. So I can stop here, and I thank you for your attention.
Well, thank you, Cristina. So yeah, as usual, you have to applaud for everyone, but okay.
Okay.
Well, thank you very much. Is there any question or comments? So if you want to ask a question, please feel free to open the microphone and ask the question directly. And if you do not have any microphone, you can ask the questions by chat and then we'll tell them again.
Yes.
Morgan?
A question, yes. Hi, Cristina.
Hi.
I have a question on the asymptotic behavior. So the whole algorithm you gave is to ensure that the coefficients are non-vanishing.
Yes.
So how do you recover that they have the good asymptotic behavior?
The fact is that when you compute the algorithm, you have more information on the behavior of the coefficient. So just looking at some coefficient, you know that they have the right behavior. So it is from the algorithm that you know there are some coefficient that tells you the behavior.
Okay, so for instance, in your example with a Robin condition, you gave that the potential you create satisfy the condition in 1/k, and do they also satisfy the stronger condition?
Yes, and I don't remember. I should look into the paper, but it is very easy to prove the behavior. There are some coefficient that tells you, and maybe I can send you the references. But it is always satisfy also the behavior that it is required. There are some coefficient, I don't remember which one, but it is very easy to prove also the behavior.
Okay, thank you.
Welcome.
Is there any other question? Okay, I will ask one. So for the conditions you are looking on your potentials mu, I was wondering, is it some kind of generic condition? Because if I remember correctly, the article by Bouchard and Loreau, their condition is somehow generic, right?
Yes, yes. But the fact is that the nice thing would be to have also necessary conditions, so you completely determine the set of. But the fact is that it is very, very difficult to have also necessary condition. So what we could do is just to give sufficient condition. So using the algorithm, you know that you are safe, but if you have some polynomials and you try to see if it satisfies the algorithm, and it satisfies, it's okay. If it does not satisfy, you cannot say anything. So yeah, the fact is that there are a lots of these function that satisfies, but it's difficult to characterize. We have also proved this condition not only for polynomial, but we succeeded also with the trigonometric function and also with the exponential. So the key formula, the first two formulas that I show you that are very important also to characterize functions that are different from polynomials and that satisfies this condition.
Okay, thank you.
Omar has a question. Omar Budak, can you open your microphone, Omar?
Okay, thank you very much. Thank you very much for your presentation. It is very interesting. I have a question about the control of semilinear equation and bilinear control.
Yeah.
Is there some relationship between control of semilinear equation and bilinear control? Thank you.
Yeah, of course, there is a connection, and there are papers, for instance, by Bouchard that deal with this kind of non-linearities that can be bilinear control or other kind of bilinear or non-linearities. So there's a connection, and also there are results on this side.
Is that okay, Omar?
Okay.
Okay, I have a small question. Before, thank you very much for your talk. I think I have liked a lot.
Thanks.
My question is, have you looked at any extension of the ideas to multiplicative control on the boundary?
No, not yet. So you mean a multiplicative but control but at the bound? No, but yeah, I should look at. Yeah, it's one of the things I should think about.
Okay.
But sorry, is it okay? Yeah.
Okay.
But in the case of a non-bounded control operator, what would be what would be the difficulty in the case of an unbounded control operator? I mean, for the theory, the condition would probably be the same, right?
Yeah, we already treat the unbounded case. The difference being in the space where you control. So there will be some power of the domain of powers operator of A. But you can have similar results of controllability and stabilizability also for unbounded operator. We did it. We already did it. Yeah.
Okay.
Silva?
Yes, Lassen?
Thank you very much for this nice talk.
Thank you.
Is there any result about boundary bilinear control?
Boundary bilinear
That
control.
means B is in some negative subpolynomial space.
This I don't know.
Okay, thank you.
Okay, is there any more question? Well, so I think it's okay. Well, thank you again, Cristina.
Thank you. Thanks.
And okay, we'll jump to the next speaker, Wencel. So we have well, 1 or 2 minutes just to upload the thing. Belassène, you wanted to say something?
Juste applaudir.
Ah, ok.
C'était sympa. C'était très bien.
Okay. So that looks nice. Very good.
Can you see my screen?
Yeah, the screen is perfect.
Great.
So I guess we can start, man. Are you ready?
Yes, sir.
Okay, so next speaker is Wencel Valega Mackenzie from University of Tennessee, Knoxville. And he will speak about resource allocation in an open ecosystem. Thank you.
Thank you for the introduction there. And so thank you also all of the organizers of the seminar for giving me this opportunity to present my research here today. Okay. So we're going to kick off with the content of my talk, which includes some motivational background, some aims. Then we will give an outline of how to set up optimal control problems with PDE. Then I will define my resource allocation model, and then we will go into some details there. And later we will show some numerical simulations just to illustrate the dynamics of the model. Okay. So we're going to start off with the usual logistic model. And here we have R, it's representing the intrinsic growth rate, and K, it's representing the carrying capacity. So when we assume that R and K are constants, then we can plot some of the solutions for this differential equation here at different levels of intrinsic growth rate, and setting the carrying capacity equal to 10 and 2 different sets of initial conditions. So you can clearly see that since the intrinsic growth rate is positive, as time goes on, the total population will approach to that stable steady state, which is K in this case. So if we switch the sign of the carrying capacity, then we will see that the total population will approach 0. So, but one thing to think about is that just by looking at the differential equation and the graph, it doesn't seem to be a relationship between the intrinsic growth rate and the carrying capacity. So one way that we could see maybe a better relationship between R and K to be separating the per capita growth rate of the population as a linear density dependence between birth and death. So if we take this equation and rearrange it, we can get back to our logistic equation, and here we can see that our intrinsic growth rate and carrying capacity are related, right? They seem to be proportional. Another way that we can include this approach could be using a more mechanistical system. So we're going to consider this resource limited system here, where N is the total population, the population density, and R is its resources. So by adding these 2 differential equations here, and then integrating the sum over time, then we can solve for R, this equation here, and substitute that back into our differential equation for N and recover the logistic equation, okay? And then one more time, we can see that there is a relationship between the carrying capacity and the intrinsic growth rate. In this work, we're interested in such relationships and ideas of resources having their own dynamics in a PDE setting, so that we can allow habitat heterogeneity in space and time. So it is important to know three things here. For example, the effect of heterogeneous habitat on a diffusion population is crucial to understand population dynamics. Loreau, in his book From Population to Ecosystem, identified an increasing gap between community ecology and ecosystem ecology. One aspect of the problem is to understand how the spatial and temporal arrangement of favorable and unfavorable resources might affect the population growth. So we're going to review some mathematical papers that are tackling all of these ideas. So we're going to start with this paper in 1991, written by Cantrell and Cosner, and they study the steady state of a population who could diffuse through the habitat via random walks with linear or logistic growth rate and spatially dependent coefficients. So here D represents the diffusion rate, M is what they consider the intrinsic growth rate, and C is the carrying capacity. So in this paper, they examined a number of one-dimensional cases where the intrinsic growth rate could have a positive sign, which means a positive effect in parts of the habitat, and also a negative effect everywhere else. Okay. Later, in 2016, DeAngelis and other authors analyzed the properties of the positive steady state of this problem here in 6. So they mainly focus on properties of the steady state solution of that system in terms of the intrinsic growth rate and the carrying capacity. In particular, they wanted to know when this integral inequality holds. In other words, this integral here represents when is the total population steady state much larger than the total carrying capacity. And now adding a little bit of control to our review papers, we consider this recent publication by Baines and Lenhardt, where they consider an optimal resource allocation for a population who could diffuse and have logistic growth, and also a resource function that could depend in space and time, okay, rather than just space. The goal of this optimal control problem is to find an optimal resource allocation function in this set here, B of admissible controls, such that they could maximize the total abundance of the population at the final time, the total abundance of the population in the entire habitat, and they want to minimize the cost of allocating those resources. And then that maximization problem there, it's going to be subject to this differential equation here in 7, okay? And something to point out here, it's the previous paper, they were studying the same equation here in 7, but in steady state. And in this one, they are considering not steady state. So we still have to carry on with the use of T term there. So before we have elliptic problems, and now we have a parabolic problem here. So taking into account the gap that Loreau considered between this ecosystem and community ecology and the previous papers that I've just mentioned, then we would like to formulate a reaction diffusion population model to study the effect of resource allocation in an open ecosystem, allowing resources having its own dynamics in space and time. Moreover, we would like to develop an optimal control problem of our resource allocation model such that we can maximize the abundance of a single species. And at the same time, we want to minimize the cost of the inflow resource allocation. So before I define the model, I want to tell you the outline that we will follow to set up our optimal control problem with PDE. So the first thing that we need to do is we need to choose a solution space for our states. Then we have to choose also a set of admissible controls, and we need to define our parabolic PDE subject to initial conditions and boundary conditions. And then we define the goal of the problem, which is probably find an optimal control in the set of admissible controls such that you can maximize or minimize an objective functional subject to your PDE problem. Then after that, one need to show that given an admissible control, we should also have a relationship between the admissible controls and the state. Okay, so we need to show that dependency, and to show that dependency, we require a priori estimate of the states in the solution space that can justify convergence of a maximizing sequence and then prove the existence of an optimal control. We will derive the necessary condition for our optimal control problem with PDE by finding the corresponding adjoint and sensitivity PDEs. And also we will use those adjoint and sensitivity PDEs to determine an optimal control characterization. Here in this talk, I will illustrate step 5 and 6, and then something that you could do after you have found the optimal control characterization is that you could show that the optimal control is unique as long as time is sufficiently small. So here's our model, our resource allocation model with diffusion population. So basically, N here represents the population density. R is the amount of resources that the population can have. D is the carrying capacity. D is the diffusion rate. Alpha 1 represents the conversion from resources into population growth. I here is the input amount of resources, and it's going to be what we will consider later as the control. Okay. Alpha 2 represents the rate of loss of resources due to the population. The term P times mu times N, it's the contribution to the resources from the death of the population. And Q here, it's our resource decay rate. Okay. All of the parameters in our model are going to be assumed non-negative, and our function I is going to be bounded in our domain Q. Okay, so we're also considering zero Dirichlet boundary condition, which just basically means that as the population approaches the boundary, it will die out, right? Because there is nothing there. Okay, and these are our set of initial conditions. Okay, so we're going to analyze this special case to connect with this idea of carrying capacity and intrinsic growth rate, and show that our model also connects with those ideas. So under these assumptions on the parameters of our model, then we can reduce our model to this differential equation here. Then we will carefully integrate over time and rearrange such that we can solve for R. And now using this expression here for R into and substitute that back into our differential equation for N, and doing some algebra there, we can recover our usual logistic equation. But now here, the intrinsic growth rate and carrying capacity depend on space and time, so they are no longer constant. And we can see that there's still a relationship between the intrinsic growth rate and the carrying capacity. They seem to be proportional, okay, under these circumstances. So now a little bit of more about the weak formulation. So since we're going to follow the guidelines of how to find solutions of this optimal control problem, so we should require some weak formulation, since classical solution might not exist for this problem with optimal control. So we gave here the definition of what a weak solution is for our problem. Okay. And subject to initial and boundary conditions. Okay. So we have shown on a priori estimate, and here I will just read them to you. So basically, lemma 1 states that the weak solutions of our problem will be non-negative as long as the initial conditions are positive and bounded. Lemma 2 and lemma 3 states the existence of uniform bounds for our state n and time derivative of n in their corresponding solution space. Okay, here is the optimal control problem that we're formulating. So basically, we choose our set of admissible controls U, and then our goal here is to find a optimal control such that we can maximize the total abundance of the population, and we want to minimize the cost of implementing that control. Okay, that's what the maximization problem is referring. Subject to our resource allocation model. So I'm going to give you a sketch of those step 5 and 6 that I mentioned before. And the idea is to begin with, so given an admissible control, I want to find another admissible control I epsilon. And then we will then differentiate the map that goes from I to N and I to R. Okay, so step 2 is just showing that given a control, there should be a corresponding state solution, right, for that control. And in step 3, we want to take the limit as epsilon goes to 0 of the difference quotient between those two states. And this limit here converges weakly to psi 1, which is, and then we do the same for R. We build the difference quotient and pass the limit, and we need to show convergence there. All those convergence results have been proven. So, and that limit converges to psi 2. Now, psi 1 and psi 2 are what we call the sensitivity of the N and R equations. So we're going to do something similar now with the PDE. We form the PDE difference quotient between N epsilon and N. And then in step 6, we pass the limit, and we have to show that there's convergence of all those terms. So we've done that. So and then we obtain a PDE problem for psi 1, okay, which is right here. Once you carefully pass the limit, then you can obtain this system right here. We do the same. We form the ODE difference quotient between R epsilon and R, and pass the limit using those convergence results that we have found. And then we obtain an ODE problem for psi 2, which is right here, which is the sensitivity associated to the state R. Now, we put together our PDE our PDE problem for psi 1 and our ODE problem for psi 2 in vector form. And this problem here is a linearized version of the original resource allocation model. Okay. Now with the linearized version, we see here that we have an L operator, and we can find an adjoint operator L star by multiplying formally lambda 1 times the L1 operator applied to the function psi1 and integrate over the domain Q. We repeat the same with lambda 2 and multiply that times lambda times L2 applied to psi2, and we can connect the sensitivity with the adjoint system. Okay, and here we have omitted a lot of the steps, but basically here this is the adjoint system. Something to point out here is that the adjoint system is related to our objective functional. How? The right-hand side, the vector on the right-hand side, the first entry is the derivative of the integrand of the our objective functional with respect to the end state, and the second entry is the derivative of the integrand of our objective functional with respect to the R state. So now we're ready to define an optimal control to differentiate the map from I to J. And so what we're going to do here is that we're going to assume that there is an optimal control, and we're going to create that I epsilon other admissible control. And then one thing to notice here is that this difference quotient, since I star is an optimal control, must be less or equal than 0. Okay, so here we carefully pass the limit. Okay, epsilon goes to 0, and then we see that the first that this difference quotient here will approach to psi1. This one here will approach to k times c3, and this one here will approach to 2 times I times k. Okay. Now we save this second term inside this integrand, and we switch the form of the first term. You can write it as in this dot product form, and between these two vectors. And then here we notice that this vector is the right-hand side of our adjoint system. So that's what we did here in this line. And then from this line to this one, we use the connection between the adjoint and the sensitivity system. And then this is the right-hand side of the sensitivity system, which is this vector 0k. You perform the dot product and factor out k, and then you get this form here. Okay. Now, to find the optimal control characterization, you must take into account the bounds for the admissible, the optimal control, and also the inequality that we got here. So if you do those two things, then you should get this optimal control characterization. So theorem 1 here states the existence of the optimal control I star. So remember that in step 11, we were assuming that there was an optimal control. So actually, we can prove that there is an optimal control, and it has corresponding solution states N star and R star, and the objective functional is maximized at the optimal control. And moreover, we could also prove that if the optimal control is unique, as long as time is sufficiently small, and C2, which is that constant next to the quadratic part of the control, is not 0. Okay, so some numerical simulations, just to illustrate the dynamics of the model. We're going to assume here that the natural death in the population and the resource decay rate do not happen. So that's one condition. And the other condition is for our purpose, our space domain is just from 0 to 1, and our time domain is from 0 to 1. Okay. So this is the system that we get after applying all of those conditions and subject to 0 Dirichlet boundary condition. Okay. So I will give you 2 numerical examples. One of them, we're going to assume that there is no input amount of resources, so that I function is equal to 0. And also assuming that this alpha 1 and alpha 2 are the same. And the next one will be using some added resources, just depending on space, not time, and also considering that alpha 1 is different than alpha 2. Okay, so here is the set of initial conditions. So the blue curve here represents the initial condition for the population, while the green curve represents the initial condition for the resources. And you can see here the pink curve is just that there are no added resources. So with this set of initial conditions applied to the model that I showed earlier, then we have this figure here, which has 3 levels, and each of these represent different diffusion rates. So the first one, it's when diffusion rate is equal to 1. This one is when diffusion rate is equal to 0.1. And this one when diffusion rate is 0.01. So the main thing that we can see here is that when the diffusion rate is too high, the population is spreading out and it's dying out and it's reaching the hostile boundaries. And the resources, they haven't been consumed, so they remain the same. However, when the diffusion rate is lower, so we allow the population to take some time and go over and find the resources, we can see that improve the population size at a longer time. Okay, so we see here that population size is increasing as time goes on, since it goes to parts of the habitat where resources were there for the population to consume them. In this second example, we consider this new set of initial conditions, and now something to see here is that now we have added resources, and now we have a different set of initial conditions for R and N. So I omitted the case when the diffusion rate was 1, since there was nothing interesting to see there, due to population will approach quickly to 0 and it will die out. But when the diffusion rate was lower, then we could see more interesting dynamics. For example, here we could see that the population, it's starting to move toward areas where there were resources, and then the population size increased. Okay. Okay, some conclusions of this work. It's that all of the a priori estimates, as well as our theorem 1 and 2, have been proven. The previous numerical scenarios were just to illustrate the dynamics of the model, and we have performed some numerical simulations using the optimal control as well. And yeah, so we didn't have to choose the initial conditions or that we chose to illustrate the dynamic of the model. So those were just, I don't know, because that was the day when I was in numerical simulation that I decided to do it that way. But we could include the natural death in the population and the decay in the resources. There's no reason why we should not include those. And later, maybe we would like to fit our model to more real world example. Okay, here are some of the references, and thank you very much for listening. Any questions?
Thank you.
Thanks.
Is there any question? I think there's one by Jean-Pierre Puel. Right, Jean-Pierre? You can open your microphone. Yeah. You have to open your microphone. We cannot hear you.
Hello. Can you hear me?
Yeah.
Yes, I can hear you.
Yes.
Did you study the case where you may have some diffusion also in the resources?
We haven't, yes, but that's something that we need to do in case of maybe looking at sample where resources can move and have some diffusion. Yeah.
And I think there are two cases where the one where you have the same diffusion parameter and you can have also a different diffusion parameter for the resources, which would be natural. Yeah. Okay. Okay.
Okay, is there any more question? So of course, if you have a question, you feel free to open the microphone and ask. Well, okay then. So probably we'll stop there then. Jean-Pierre again? No? Okay. So
I would like to say that thank you to the speaker, because it's been a very nice talk, and thank you very much. Just this.
Thank you.
Yeah. So thank you all, and well, so thank you, Wencel, thank you, Cristina, and well, both speakers will send their slides, so that they will be on the website soon, normally.